thing.
All right. Good afternoon. Any question before we start? So we are still reviewing the material that we have learned on mechanics of strength of the material. So what we covered so far, if we are given with a beam like this, which is under some axial load, for example, just one F. Here, we can find the critical section, which is the section the failure is going to occur most likely on that section. And then we are going to start doing the analysis and design for that section. So we learn how to draw the bending moment diagram, moment X, and this axis is representing moment. This axis is X. This axis is Y. And this axis is Z. So for this case, it's going to look like this. So we learned that we can see that the critical section occurs at the middle point. So we need to do the analysis for that section. So if I draw the section here, this is the beam, axis Y, axis X, and axis Z. If this is the cross section, if you look from this side, this axis is going to be Z, which is going to represent this, and this axis is going to represent Y, which is representing this one, and X is coming out of the plane. Now, the question that we should answer is, if this guy is under this loading, on the extreme side, it's going to bend it like this. So due to this loading, you will see bending something like this on the beam. So it's going to bend it like this. Now the question is, what kind of stress this bending moment is going to create in this section, which is the critical section of the beam. So let's do it as a part of class activity. First of all, answer this question. What is the direction of the bending moment? If this is under bending moment, what should be the index of M? X, Y, or Z? And then, what kind of normal stress can you see applied to this cross section, which is located at middle of the field? Do you see tensile or compression?
cool. It's me.
Okay. What do you think, Zach?
Uh,
What should be the direction of moment?
I think it's Z. It's rotating about the Z axis.
Okay, Z and so MZ. And what kind of stress do you see over there?
Above the center line, it's compression, and below the center line, it's tension.
So you are saying that here compression,
No, the other way around.
tension, and compression.
Yes.
All right, different thoughts. So look at the moment. It's going to bend the beam in this direction. Just put your finger in the direction of bending. So your thumb is gonna show the direction of moment. It's coming out of the plane. If you want to bend it in this direction, my thumb is gonna be in the positive side of the Z, so it's gonna be positive MZ. And as you can see, if it's bended like this part of the beam is under tensile because it has been we have elongation on the length, so it's gonna be under tension. But upper side of this line, it has been compressed. So we are gonna see the compression. So then we have MZ. It's gonna generate normal stress, which has the direction of X, because normal stress is applied to the plane, coming out of the plane, and the plane has the axis of X. So when the cross section is under bending moment, we are going to have the neutral axis on the cross section. So if this is Z axis and this is Y axis, the question is, where is the location of neutral axis? You should look at the cross section and find the centroidal axis of cross section. So if you find the centroidal axis of cross section, you can find the location of neutral axis. The neutral axis here, whatever is the axis of normal stress is going to be that axis. So axis X should locate at the centroidal axis of cross section. For this rectangular, it's going to be at the middle. So axis X, which is the neutral axis, is coming out of the plane at this position. If I have something like this, the circle is going to be again, centroidal axis is going to be at the middle. For different type of cross section, like this triangle, the centroidal axis is located h over third from the middle, and this distance is b over third. This is b, this is h the height. So for this quarter part of the circle, we can find G, which is the centroidal axis of this cross section at table A18. How can we find Y bar and Z bar, which are the coordinates of the centroidal? It's going to be the integration of Y dA over A, and for Z bar, it's going to be integration of Z dA over A. These are valid for the continuous cross section like this or this. I don't expect you to do this integration but if you are given with something like this, which is a combination of some rectangular or something different like this T-shaped cross section, the question is where is the location of centroidal? Then you need to do this. I will go through the example, but this is how we can find y bar. Y bar means if this is 0, 0, how far should I go up in y direction to put the axis? This is how you can find y bar. The summation of y bar I times ai, I have 1, 2, 3 cross section. Where is the y bar 1? It's going to be at the middle, this way. Where is the y bar 2? It's going to be at the middle of this height. And where is the y bar 3? It's going to be this height. Times a1, a2, and a3, and then divide by 8, you will find y bar. Same thing for the z bar. We will do to find the location of z bar. In this case, since we have symmetry, we don't need to find z bar. Z bar is going to be at the middle, just right here. Same thing here. Z bar is here, we need to find y bar. Anyway, after you figure out that location, we can put the neutral axis at that point, which is the centroidal axis of cross section. Then the sigma has this relation with m. If we are given with mz, which is the maximum bending moment at the middle of the beam, if you are looking for a normal stress at this point, what you need to do, you just need to measure the y distance of this point from the centroidal axis, which is this distance. If the point is here, the y is going to be this. If the point is here, the y is going to be this, but negative, because it's below the positive side. So whatever is the y coordinates of the corresponding point, multiplied by mz, divided by second momentum area. With respect to which axis? Whatever is the axis of z, whatever is the axis of moment, it should be the axis of momentum area. With respect to moment axis, whatever is that. So it's going to be mz times y divided by iz. But we need to add one negative sign here. Why do we need to have one negative? Because just consider a point on the top of this line. One point on the top of this line. The y coordinate is positive. So, and m is also positive. As you see, m is positive. Positive times positive, and iz is always positive. So you will get a positive number. But we know that any point on the top of neutral axis is gonna see the compression. So we should get the negative sign for the normal stress. So it's the reason that I need to put a negative sign here. For the point, for any point below this line, y is gonna be negative, m is positive. So negative times this negative, you will get positive normal stresses, which represent the tensile stress on any point below the this line. We have neutral axis, we have neutral plane. Whatever is the axis of moment is gonna represent z, and whatever is the axis of this plane, which is x, is gonna represent neutral plane. So the plane passing through the neutral axis, just imagine a plane on zx direction passing through this axis. It's gonna be this plane. So this plane, it goes all the way through zx. It goes all the way through this middle of the beam. So any point in this plane is gonna see the normal stress equals to 0. Sigma equals to 0 at any point of neutral plane. So if I ask you what would be the stress at this point, since the point is located on this plane, it's going to be 0. Same things here, same things on the other points located on plane zx. So these are some points that we have seen, and the I with respect to z-axis is going to be the integration of second moment of area. This is the moment of, this is second moment times dA. It's going to give me second moment of area over entire of this cross section. If this length is h, this length is b, bh. Iz would be b times h power 3 divided by 12. For cross section, if this is z, for cross section, for circular cross section is going to be pi d power 4 divided by 64. So for any other cross section, you can calculate that integration, but basically we are working with circular cross section and rectangular or combination of some rectangular cross section. But in general, you can use this integration to find the second moment of area about the axis. Any question on this before I ask you to work on the class activity? All right. Now, here I applied bending moment about z-axis. I made a bending about z-axis. What if I make moment about y-axis? Just try apply a force in this direction. Try to bend a beam in y direction. My thumb is going to y direction, so we are going to have my. Instead of mz, we are going to have my. Revise this equation if we have y, a bending moment about y-axis, not z-axis. How should we revise this equation to provide the normal stress for critical section? So just imagine at this beam we have bending moment about y-axis as well. find a equation for this. Is that clear?
I was trying to copy the notes over there. Could you go back to it and I'll just kind of guess?
Okay, let me. Number 41. What do you think? Just if here we have z, here I have y. So if here I have y, why should I have here? And if I have z, since this should be the same, it's gonna be I, y. Okay? Just imagine about y. It's gonna make bending on the beam. Think about the cross section. The beam is gonna bend it about y-axis. Can you imagine? I mean, it's gonna bend it about y-axis. So this portion is gonna see tensile or compression. If it's bended in this direction, this side is gonna see tension, and this part is gonna see compression. So any point on the left side is gonna have positive z, because positive z-axis is gonna be in this axis. So z is gonna be positive. M is positive because it's bended about positive y-axis. So positive times positive is going to give me positive. And it should be positive because it makes the tensile. So I don't need to add negative sign behind that. So the only difference between this and this one is the sign. Just think about any point on the right side. Any point on the right side has negative z because it's going to be on the right side of y-axis. So negative z times positive give me negative number, which represent the compression. So this is, if I have a moment about y-axis is going to give me normal stress by applying this equation. If I have bending moment about z-axis, it's going to give me the normal stress based on this equation. This is I with respect to axis of rotation, which is y. This is I with respect to axis of rotation, which is z. Look at this triangle. IZ, if you do the calculation, it's going to be b times h power 3 dividing by 12. If I ask you to write IY, I with respect to this axis, then it's gonna change to b power 3 h 12. So as you see, they are different. So make sure that you use the right equation. But for the circular cross section, as you see, we have symmetry about y and z axis. So both have the same value, pi times d power 4 divided by 64. Any question on this? It has many details, so I'm just trying to explain all details before we start working on the exam. Alright. If we only have m about z-axis, if I ask you, we only have m about z-axis. If I ask you at which points of the cross section we are going to have maximum sigma max, you look at this sigma max, mz is constant because it's going to be the same for any point in this cross section, because moment has one value for any point in this critical section. So all points, they have the same moment. Iz is going to be the second moment of area for this cross section. It's going to be the same. The only thing which is varying is y. Different points, they have different y. So if you are looking for the maximum y, the y occurs at y max. So if I forget about the sign, the greatest value is gonna happen when y getting its maximum value. What's the maximum value? It's gonna be on this line and this line. So any point in this line with the y of, if this is h, half of the h is gonna get the maximum sigma, and any point in this line with the maximum y, which is negative h, is going to get maximum sigma. We know that this point they will see compressive, this point they will see the tensile stress. So, but it occurs at this line and this line. For my, the maximum occurs in these two extreme lines. I mean here and here, which has at z max, which is b divided by 2, half of b. So this is another thing. If the maximum distance is called c, which is half of the b, then we can say we call this z or section modulus. It's just definition, it's not. Here, Iz is going to be h power 3 dividing by 12, but b is this length, h is this one. So, just revise. Here I was use the correct letters, but over there I switched b and h. So h is the height and b is the width of the cross section. All right, now I labeled 9 points. 1 at the corner, 2 at the middle, 3, 4, 5, 6, 7, 8, and 9. These are 9 points on this critical section of the beam. If this is under MZ and MY, it's under both bending moment. Tell me which points it's gonna see the maximum tensile, which point is gonna see the maximum compression. And which point has zero stress. Any question about this?
This. Yeah. This way.
Number 36. Based on just if you look at MZ, which point do you think it's gonna see the tensile? Point C. Do you see any other points? Point 7 and point 5 also, they will see the tensile stress because they have the same y distance from this axis. So 0.5, 6, and 7, they will see all tensile. And 3, 2, 1, they will see all compressive stresses because they have the same distance from the neutral axis. Number 25. So, what do you think? Pardon?
8, 9, and 4.
It's gonna see the maximum tensile?
No.
0 stress. Say it again, 5, 9, and 4.
8, 9, 4.
8, 9, 4.
Yeah.
894. I agree with you if it's under only MZ. If it's bended in this direction, this axis is gonna be the neutral plane. So any point on this line is gonna see the 0. But we have MY, which makes some stresses non-zero.
Dr. Gazi, can I just answer it?
Sure.
Peak tensile is going to be at 0.7, peak compression is going to be at 0.3, and then you're going to have a neutral axis of sorts going from 1.9 and 1.95.
So 0 would be 3 points.
Yeah, 0 would be at that.
1,
1, 9, and 5.
Any different out,
0 is only at the center.
which is 9.
Okay, I can't read your numbers that far away. I think I labeled mine different. So.
So 0.9 is at the middle. I mean central.
Okay.
Different out.
One is going to be maximum compression, 5 is going to be maximum tensile, and 9 is 0 stress.
9 is 1 and 5 and 9. 1 is tensile
Yep.
and 5 is compressed.
Other way around. That's right.
5 1.
Yeah, 5.
Okay, let's see. Just think about MZ. MZ, neutral plane. Any point on this line, on this plane is gonna see the 0. On the top of that, just think about compression. And here we are gonna see the tensile. If we bend in Z direction. Now, if I bend in Y direction, just positive Y. This is gonna represent the neutral plane, which is at the middle. The right side is gonna see compression, and left side is gonna see tensile. Now, point 1, point 2, 3, 4, 5, 6, 7, 8. Which point see both tensile stress maximum? Point 7 is gonna see the maximum tensile here, and is gonna see the maximum tensile because it has the greatest distance from this axis. So point 7 is gonna see the maximum tensile stress. And this, at MZ, which point is gonna see the maximum compressive? Point 1, 2, and 3. Which point is gonna see the maximum compressive here? 3, 4, 5. The common point is gonna be point 3, which is gonna be this. So point 3 is gonna see the compression, the maximum compression. Any point in this line is gonna see the 0. Any point on this line is gonna see the 0. The common point between these two would be only the center point, which is point 9. So for other points, you will have some values, which is non-zero, and the maximum tensile is gonna see here, and the maximum compression is gonna be at point 3. Good. This is important because in some mechanical components like beam, you might have different loading, different bending moment. Then you should figure out which point is gonna be the critical point, or the failure if it wants to happen, at which point is gonna occur. So then it's gonna occur either at point 3 or 7. So this equation, if one beam is under both mz and my bending moment, the normal stress at any point can be obtained by this equation. So suppose I would like to find the bending moment, normal stress due to the bending moment at this point, which the coordinates of y1 and z1. Coordinates is z1, y1. So it's gonna be sigma, whatever is mz times the coordinates of y, which is y1, divided by iz plus my times whatever is the coordinate of z, which is z1, divided by y. Just for circular cross section, we don't use this equation. For circular cross section, what we will get, if you remember on this example that we did, since we have my and mz on the circular cross section, we can find the summation of the moment, which is s square root of my square plus mz square. So we will get one bending moment. Then after we find one bending moment, which is this, we look at the other value, which is c, half of the radius, and the I, which is, we know that I times d power 4 divided by 64. So for non-circular cross section, we use this. For circular cross section, we are using this equation. All right. Now let's look at if I have a cross section like this, with the size of 80 millimeter, 8 millimeter, 120 millimeter. These are the same, 8 millimeter, and this is 8 millimeter. The cross section is look like something like this. It's under mz. It's under only bending moment in z direction. We know that maximum allowable stress is 150 megapascal. So the cross section cannot support any stress more than 150 megapascal. So it means the maximum stress applied to this cross section should be less than or equals to 150 megapascal. Find maximum allowable moment. What would be the maximum bending moment that you can apply to this cross section if the maximum allowable stress is 150? So to find that, you need to find the maximum normal stress. The maximum normal stress occurs at the highest distance, greatest distance from centroidal, from the neutral axis. But where is the neutral axis? Y-axis is going to be here because we have symmetry, but for z-axis, we don't know where should I put the z-axis for the neutral axis. So we need to find or calculate that based on the equation, based on the sigma equation that I wrote at the beginning. So So if this point is the origin, 0, 0, I would like to find what would be the y bar of z axis, at which location of point 0, 0 I should draw the z axis. So basically I'm looking for y bar, which is summation of 1, 2, 3 ai times y bar divided by summation of all three cross sections that we have over there. So we have one rectangular here, another rectangular there, and third rectangular over there. So for cross section 1, y bar is at the middle of this rectangular, which is 60. For second cross section, if I ask you where is the centroidal location of the neutral axis, it's going to be 8 divided by 2. It's going to be 4 millimeter, and y bar 3, same as the first one, it's going to be 60 millimeter. A1 is 8 times 120. A2 is, this is 80 millimeter, this is 8 millimeter, 8 millimeter. So this length is going to be 64. 64 times 8, and A3 is going to be 8 times 120. So if you plug in the numbers there, you can find y bar. I will continue this example on Thursday.